Hi everybody, in this video we will be talking about gaseous reactions and how pressure and volume can be applied to reactions. In this example, 2 moles of methane gas and 7 moles of oxygen gas are reacted, and the end product has a total pressure of 2 atms. So what I want you to find is the partial pressure for each and every gas that exists. So think of it like this. This reaction is happening in a container, and after the reaction is finished, the container has a final pressure of 2.00 atms. So this is a limiting reactant problem. So let's do what we know first. We can find the limiting reactant, which is either methane or oxygen. So let's try to figure out how much product each of them can make. 7.00 moles of O2 can produce 7.00 moles of H2O because they are in a 2:2 ratio or 1:1 ratio. So if you have a number of moles of O2, then you will get the same number of moles of H2O because they are in a 2:2 ratio, which is a 1:1 ratio. Now, if you have 2 moles of CH4, how much moles of H2O can you make? Well, for every 1, you get 2, so it's twice as much. It's a 1:2 ratio. So this would be 4.00 moles of H2O. And we just found our limiting reactant. The limiting reactant is methane because methane produces less product. So as a result, we can make a table to tell us how much of each product, our reactant, is left over after. So this is methane, this is O2, this is CO2, and this is H2O. And after the reaction, since CH4 is our limiting reactant, then all of it will be depleted, so this will be 0. And the products, we know that since methane is our limiting reactant, then this reaction will produce at most 4 moles of H2O. So let's write 4.00 moles of H2O. And how many moles of CO2 will it make? Well, if it's a 1:1 ratio, then for every 2 moles of CH4 that is depleted, 2 moles of CO2 will be produced. So we can write 2.00 here. Now, how much O2 is left over? Well, if 2 moles of CH4 are used up, then according to this reaction, twice as much O2 is used up because it's in a 1:2 ratio. So if 2 moles of CH4 are used up, then 4 moles of O2 are used up. And therefore, if we have 7 at the beginning and we lost 4, then that means we have 3.00 moles of O2 left over. So we found the moles of each substance at the end, and notice how we have the final pressure at the end. So thinking to the last video, we derived a formula that said the partial pressure for gas A is equal to the mole fraction for gas A times the total pressure. So what do you think we will do? Well, we're going to find the mole fraction for every chemical. For CH4, the mole fraction is 0 because 0 over the total, which is 3 plus 2 plus 4, which is 9, is 0. So 0 over 9.00 is equal to 0. And let's do it for O2. So for O2, we have 3.00 moles of O2 over the total, which is 9.00 moles, and we end up with an answer of 0.33333, and I'm going to keep track of my sig figs by putting the line there, and later on you'll see why I add extra sig figs, and this should be a common habit. You should always add extra sig figs after your calculations, because if you're going to use them later, it's better to keep extra sig figs so that your answer is more accurate. So let's do it for CO2. For CO2, we have 2 moles of it, so 2 moles of CO2 over 9 moles of the total number of moles, and this gets us 0.22222. Last but not least, for H2O, it is 4.00 over 9.00, and this is equal to 0.444 underline 44. So I'm keeping track of my sig figs, and notice how this 0 has no sig figs, because if I wanted to add a decimal and add more zeros, notice how none of these count as sig figs, and this answer has 0 sig figs, so leaving it as 0 is perfectly okay. So now that we have the mole fractions, so let me actually write the mole fraction. So I have to put the X and the chemical as a subscript, and let's calculate the partial pressures for each gas. So the partial pressure for methane gas will be the total pressure, which is 2.00, which was our total pressure at the end, times the mole fraction, which is 0, and that gives us 0 atms. And our pressure for the O2 is going to be equal to 2.00 times the mole fraction, which was 0.333 underline 33, and we get an answer of 0.667 atms for the partial pressure of O2. Now let's do the partial pressure for CO2. This is just equal to 2.00 times, let's see, 0.22222, and this is equal to 0.444 atms. Last but not least, the partial pressure for H2O will be, let's see, we have to start with the total pressure first, 2.00 times the mole fraction for H2O, 0.444 underline 44, and we get 0.889 atms. So these are our 4 pressures, or our partial pressures, for each chemical in the reaction at the end. So to double check your work, you want to make sure that the partial pressures for each gas add up to the total pressure, since that's Dalton's law of partial pressures. So if you add 0.667 plus 0.444 plus 0.889, you will get exactly 2.00 atms, and that is a way of double checking your work. So let me once again clear up a misconception. So these partial pressures for each of the gases are different indeed, as we can see, but the volume for each gas is the same, since they are all in the same container, and because the gases are in the same container, they will all have equal volumes. Well, maybe except for the CH4, since if the CH4 all reacted and it doesn't exist, then it doesn't have a volume. So these other 3 have equal volumes because they all belong to the same container. So just because they have different partial pressures doesn't mean that they have different volumes. Actually, if they have partial pressures, that means they are a part of a whole, and if they're a part of a whole, then they technically all share the same whole or volume. So there is a way to make them have different volumes, but you have to do something special. So in this scenario, we have to separate all these chemicals into different balloons. So let's just say we have 3 balloons, and the reason why we're not having 4 is because the methane gas all got reacted and it doesn't exist anymore. So let's just say that I separated the O2 gas, the CO2 gas, and the H2O gas into 3 different balloons. And let's just say that for each gas, we kept the pressure at 1 atm. And let's say that the temperature of each gas is kept at 100 degrees Celsius. So my question to you is, what is the volume of each balloon? Well, we know the moles for each gas because we calculated it in a table. So let's just say I want to find the volume of H2O. I know that there are 4 moles of H2O at the end of the reaction. So let's write that. 0.4, oh, just kidding. 4 4.00 moles of H2O at the end of the reaction. So knowing this, we can calculate the volume because we essentially have P, T, and N. So doing a PV equals nRT, we get 1.00 times the volume, which we don't know, is equal to 4.00 times R, 0.0821, times the T, which is 100 plus 273.15. And doing all the math and keeping track of significant figures, we get that the volume of the balloon containing the moles of H2O is equal to 0.00816 liters. So that's how you find the volume for each substance if you separate it into separate containers. But in the case before, they were all in one container, so they all had the same volumes since they were sharing the same space. So these are two different scenarios that you might encounter. Now let's take a look at something cool. So something cool you should know is that you can also read reactions in terms of liters, and that's assuming that all the gases have the same pressure and are at the same temperature. So at a constant P and T, you can read this reaction in terms of liters. So all these have to have the same pressure and temperature for this to work. So if I wanted to completely react 2.00 liters of O2, how much liters of CO2 would be produced, assuming that we are at a constant pressure and temperature for each chemical? So if this is true, then we can read this in terms of stoichiometry. So if we have 2 moles of O2 per 1 mole of CO2, then we have 2 liters of O2 per 1 liter of CO2 at the same P and T. So doing this, we get, 2 liters of O2 for every 1 liter of CO2, and we get 1.00 liters of CO2 produced. So you can read reactions in terms of liters as well, as long as what you're reading is a gas. So for example, these two were gases, so I can convert between liters and liters. But let's just say that this CO2 was a solid instead. Then I would not be allowed to convert between liters and liters anymore. I would have to look at them in terms of moles or molecules, since you can't say that for every 2 liters of O2 you have 1 liter of solid CO2, because that doesn't make sense. It only works for gases. So keep that in mind when you're doing this trick. So for example, if I said that 2.00 liters of CO2 gas was produced in this reaction, you would not say that 2.00 liters of carbonic acid was used up, because carbonic acid is aqueous and not a gas. So you have to resort to using other methods, such as converting this to moles and looking at this reaction in terms of moles in order to achieve what you want. So that's all for this video, and have a nice day.